Right now, 5 billion kilometers from Earth, a dwarf planet is radiating heat into space in a way that no gas-based model of any atmosphere in the solar system can fully account for. No spacecraft has ever measured an atmosphere colder than physics said it should be by this much. No telescope before this one has ever been sensitive enough to separate its heat signature from the moon orbiting 12,000 miles away. It is not a broken model. It is an atmosphere running on a completely different set of rules than we assumed. Stay with me, because the real story here is stranger and more carefully proven than the headline lets on. If you're new here, this channel breaks down real space missions with real data, no filler. Subscribe if that's your thing. Let us go back to the beginning. To understand why this matters, you first need to understand what should have been true. Pluto was discovered in 1930, orbits the Sun once every 248 years at an average distance of nearly 5. 9 billion kilometers, and was reclassified from the 9th planet to a dwarf planet by the International Astronomical Union in 2006, a decision that remains genuinely contested among planetary scientists to this day, and one that has nothing to do with what follows here, because none of the physics in this story cares what label Pluto carries. For most of the 20th century, everything humanity actually knew about Pluto came from blurry, distant telescope observations, a fuzzy point of light with an estimated size, an estimated color, and almost no confirmed detail about what its atmosphere was actually doing. That changed only once, in a single flyby that lasted mere hours. When NASA's New Horizons spacecraft flew past Pluto on July 14, 2015, it carried an ultraviolet instrument called ALICE, built to watch the Sun pass behind Pluto's disk and measure exactly how the dwarf planet's thin nitrogen and methane atmosphere bent and absorbed that light on the way through. From that single occultation, scientists could calculate atmospheric temperature with real precision, and the number that came back made almost no sense. Based purely on the known gas composition of Pluto's atmosphere, the standard method used to predict temperature for basically every other atmosphere we've ever studied, from Venus to Titan, scientists expected an upper atmosphere sitting around 100 Kelvin, roughly minus 173 degrees Celsius. What New Horizons actually measured was closer to 70 Kelvin, minus 203 degrees Celsius, nearly minus 333 degrees Fahrenheit. That is not a rounding error. That is a 30-degree discrepancy between what the physics predicted and what the spacecraft actually recorded, on a world so distant that getting this wrong wasn't really an option scientists could afford to be casual about, since the raw occultation data itself had taken more than 4 hours just to travel back to Earth at the speed of light. To be clear, this wasn't sloppy science being corrected. The gas-based model for atmospheric temperature is a well-established, thoroughly tested framework that works reliably across dozens of planetary atmospheres in our solar system. Pluto was simply the first place it broke. The ALICE instrument itself was a relatively small, lightweight spectrograph, built to squeeze meaningful atmospheric science out of a spacecraft that only got one irreversible pass at its target. There was no orbit, no second attempt, no chance to refly the encounter if the data came back strange. It came back strange anyway. To put that gap in perspective, predicting an atmosphere's temperature from its gas composition is not some shaky guess. It's the same basic framework that lets scientists model Earth's greenhouse effect, forecast Venus's crushing 465 degrees Celsius surface, and describe the thick orange smog choking Titan's skies. When that framework has been tested against dozens of atmospheres across the solar system and consistently gets the answer right within a reasonable margin, and then gets Pluto wrong by 30 full degrees, that's not noise in the data. That's a signal that something about Pluto's atmosphere works differently from every other atmosphere the framework had ever been checked against. For 2 years, that discrepancy sat there, unexplained, filed under atmospheric mystery in half a dozen research papers. Then, in November 2017, a planetary scientist named Shi Zhang at UC Santa Cruz, working with Johns Hopkins researcher Darryl Strobel and NASA Ames scientist Hiroshi Imanaka, published a paper in the journal Nature that proposed something nobody had seriously modeled before. What if the temperature wasn't being controlled by gas at all? Pluto's atmosphere is thick with haze, countless microscopic particles of hydrocarbon soot formed when sunlight breaks apart methane and nitrogen molecules high above the surface, then slowly settle downward through the atmosphere like an endless planet-wide smog. Zhang's team proposed that these solid haze particles, not the surrounding gas, were absorbing sunlight during the day and radiating that heat straight back into space at night, acting as an extraordinarily efficient radiator, cooling the atmosphere far more aggressively than gas molecules alone ever could. It was, by Zhang's own admission later, considered a fairly radical idea at the time. Most planetary atmospheres in the solar system are governed by their gases. Pluto's, according to this new model, was being governed by solid particles instead, something that, if true, would make it the only known atmosphere in the solar system to work this way. Here's the part that turned an interesting hypothesis into a real scientific target. Zhang's paper didn't just propose a mechanism, it made a specific, falsifiable prediction. If haze particles really were dominating Pluto's thermal balance, they should be radiating a very particular, unusually strong signal in the mid-infrared portion of the spectrum. A signal orders of magnitude brighter than anyone had previously assumed possible for that wavelength range. Read that again. The paper didn't just say, haze might explain this. It said, in effect, if I'm right, here's exactly what a big enough telescope should be able to see. The only problem in 2017 was that no telescope existed with the sensitivity to actually check. Here is where this stops being an abstract atmospheric puzzle and starts mattering for how we understand planets in general, including our own. Every rocky or icy world with a meaningful atmosphere runs on some version of an energy budget. Heat comes in from the sun and it has to leave again, or the world cooks or freezes in ways that make it uninhabitable. For nearly every atmosphere we've ever studied, that budget is calculated using gas physics, the same basic framework used to model Earth's own climate. If Pluto really does run its entire atmospheric energy budget through solid particles instead of gas, that's not just a quirky fact about a distant dwarf planet. It's proof that there's a second, fundamentally different way for an atmosphere to regulate its own temperature, one that standard climate models don't typically account for. Every haze-rich atmosphere we know of, including Saturn's moon Titan, and potentially some of the hazy exoplanets astronomers are now studying by the dozen, may be running on rules closer to Pluto's than to Earth's. Sit with that for a second. A dwarf planet 6 billion kilometers away just rewrote part of the rulebook for how scientists model climate everywhere else. Astronomers currently have thousands of confirmed exoplanets on the books, and a meaningful fraction of them show the same kind of thick, obscuring haze in their own atmospheres. Haze that has, until now, mostly been treated in climate models as background noise sitting on top of the real gas physics, rather than as a mechanism capable of driving the whole system. Pluto just became the nearest, best documented proof that treating haze as a footnote instead of a driver can be a genuine mistake. But confirming Zhang's prediction turned into one of the more frustrating scientific waiting games in recent planetary astronomy, a genuine, years-long obstacle with real stakes attached, and it almost didn't get the chance to happen at all. The telescope Zhang's paper was quietly betting on had already slipped its launch date by more than a decade and ballooned in cost into the billions before it ever left the ground. And when it finally did launch, on December 25th, 2021, it had to survive roughly 2 weeks of what engineers openly called the most complex, highest-stakes deployment sequence ever attempted in space, unfolding a tennis court-sized sunshield out of a folded package the size of a delivery van, then unfurling a 18-segment gold-coated mirror with hundreds of individual mechanisms that each had to fire correctly in sequence, with no astronaut within 1,000,000 miles able to fix anything that jammed. A single stuck hinge could have ended the mission, and Zhang's prediction before either ever got tested. It didn't jam. JWST arrived at its observing position nearly 1,000,000 miles from Earth in January 2022 and began full science operations that July, carrying exactly the kind of mid-infrared sensitivity Zhang's team had been waiting 5 years for. Astronomers pointed the telescope's MIRI instrument at the Pluto-Charon system as part of a dedicated observing program specifically designed to test the haze cooling hypothesis directly. And then, having survived the hardest engineering test in the telescope's short life, they ran straight into a problem nobody could engineer their way around with raw sensitivity alone. Charon, Pluto's largest moon, orbits at a distance of roughly 12,000 miles. Astronomically speaking, that's close enough to be almost glued to its parent world. From JWST's vantage point, more than 3 billion miles away, the two objects sit so near each other in the sky that their thermal glow overlaps. And that overlap turned out to be a serious problem because Pluto and Charon are not remotely the same kind of surface. Pluto is coated in nitrogen and methane ice, wrapped in an actual atmosphere, blanketed in that same haze Zhang's model was built around. Charon has no meaningful atmosphere at all, and its surface is dominated by exposed water ice instead. Two completely different thermal fingerprints tangled together in a single blurred signal, arriving at the same detector at the same time. As the researchers themselves put it afterward, they simply could not tell which part of the signal belonged to Charon's bare, icy surface and which part belonged to Pluto's haze. For years, that ambiguity was enough to stall the entire test. A theory that had been publicly, specifically, falsifiably predicted back in 2017 was sitting there, technically testable, practically unreadable, a signal simultaneously present and unconfirmed in the same dataset. The fix wasn't a single dramatic breakthrough. It was patient, methodical work, spread across multiple observing visits rather than one triumphant image. The team designed an observation program precise enough to separate the two signals mathematically rather than optically, since no camera, however sharp, could simply zoom in far enough to draw a clean line between two objects sitting that close together from 3 billion miles away. They used MIRI's imaging mode to capture photometric light curves of Pluto and Charon at 4 specific mid-infrared wavelengths, 15, 18, 21, and 25 micrometers, tracking how the brightness at each wavelength rose and fell as each body rotated through its roughly 6.5-day day-night cycle. A companion spectrometer, the medium resolution spectrometer, swept across a much broader band from 5 to 28 micrometers, adding composition data on top of the temperature readings. None of that raw data meant anything on its own. It only became usable once the team built a model, grounded in everything already known about Pluto's and Charon's surfaces from New Horizons, capable of predicting how much of the combined light each world could plausibly be contributing at every single wavelength, then checking that prediction against what MIRI had actually recorded. It required combining new JWST data with nearly a decade of prior spacecraft measurements just to build a model precise enough to trust. And there was no guarantee, going in, that the numbers would ever cleanly separate at all. Here's where it finally breaks open. When the researchers, led by planetary scientist Tanguy Bertrand, finished untangling the two signals, Pluto's share of the mid-infrared light didn't just match a bare, haze-free surface, it showed a distinct thermal excess. Extra brightness that couldn't be explained by the surface ice alone, extra brightness that lined up almost perfectly with the exact wavelengths and intensity Zhang's team had predicted 8 years earlier. For the first time, scientists were not modeling Pluto's haze indirectly through a temperature gap. They were watching it glow. Here is what is happening right now in 2026. That confirmation was formally published in Nature Astronomy earlier this year, closing an 8-year gap between a bold theoretical prediction and direct observational proof, a gap that spanned an entire mission's redesign, a 5-year rocket delay, and one of the most technically demanding space telescope deployments ever attempted. The same JWST observing campaign didn't stop at temperature. Researchers used the data to place real constraints on the thermal inertia and emissivity of different terrains across both worlds, distinguishing regions coated in methane ice from those covered in darker, older deposits, and mapping how efficiently different patches of Pluto's and Charon's surfaces store and release heat through each rotation. Separately, in a companion effort led by planetary scientists Sylvia Protopapa and Ian Wong using the same telescope, researchers announced in October 2024 that they had detected carbon dioxide and hydrogen peroxide on Charon's surface for the first time. Chemical signatures that had never been confirmed there before, adding new detail to a moon whose geology remains, in important ways, better mapped than any other object of its size in the outer solar system. Thanks entirely to the decade-old New Horizons flyby data these new observations keep building on. According to the research team's own account, the carbon dioxide detection matched what models expected, but the presence and behavior of hydrogen peroxide on Charon's surface is still being actively worked through. What most people are not seeing in the breathless version of this story is that none of this happened in a single dramatic Webb looks at Pluto moment. It happened as a slow accumulation of extremely careful cross-referenced measurements built on top of each other for 8 straight years. And Pluto isn't even the only target in this line of research right now. JWST has spent much of the past 2 years turning its instruments toward other icy worlds scattered through the same outer region of the solar system, the Kuiper Belt, cataloging atmospheres and surface chemistry on bodies far too faint and far too small for any previous telescope to study in any real detail. Pluto remains the best understood member of that entire population, almost entirely because of the 1-2 combination of New Horizons' close flyby and JWST's follow-up spectroscopy, a pairing no other Kuiper Belt object currently has, and the reason Pluto keeps functioning as the calibration point every other icy dwarf planet gets measured against. Every new haze detection on some smaller, fainter world out past Neptune gets checked, implicitly or explicitly, against what scientists now know happened on Pluto first. And there is more coming, on a schedule that is already locked in. On September 30th, 2026, at 8 p.m. Eastern Time, the deadline closes for scientists to submit new observing proposals for JWST's 6th annual observing cycle. Proposals will be released to expert reviewers in early November 2026. A telescope allocation committee will meet to rank them between February 1st and February 11th, 2027. Selections will be publicly announced in March 2027, and the observations themselves, whatever new targets get approved, potentially including further follow-up on Pluto's still not fully mapped haze layers and Charon's newly detected surface chemistry, are scheduled to begin on July 1st, 2027. That date is not a guess. It is a fixed point on an institutional calendar, set months in advance, waiting for whichever team of scientists makes the strongest case for why the story isn't finished yet. Every one of those proposals will compete for an instrument whose observing time is booked years ahead, split across thousands of astronomers studying everything from the earliest galaxies in the universe to planets orbiting other stars, which means a return trip to Pluto's haze layers is never guaranteed. It has to be argued for, ranked against everything else astronomers want to point this telescope at, and approved on its own scientific merits, the same way the observations that produced this year's result once were. Now, the honest part, because this story doesn't fully resolve and pretending otherwise would be dishonest. Confirming that haze dominates Pluto's current temperature does not settle a much bigger, longer-running debate. What happens to that atmosphere over the coming decades? Pluto's orbit is extremely elliptical, and the dwarf planet has been slowly moving farther from the Sun since its closest approach back in 1989, headed toward an aphelion more than a century away in the year 2114. Some atmospheric models predict that as Pluto continues cooling and receding, its thin nitrogen atmosphere should eventually begin to freeze out entirely, condensing back onto the surface as frost within the coming decades. Other models, including some influenced by exactly the haze-driven cooling mechanism just confirmed, suggest the opposite, that haze's efficient radiative cooling may actually help stabilize the atmosphere's structure against sudden collapse, meaning Pluto could hold onto a detectable atmosphere for considerably longer than the simplest freeze-out models predict. Both camps are working from real physics. Neither has been definitively proven. Adding to the uncertainty, Pluto's atmospheric pressure has actually been observed increasing over parts of the past few decades, rather than declining the way simple distance-based cooling would predict. A trend some researchers link to seasonal effects tied to the planet's tilted axis and its 248-year orbit, rather than any long-term collapse. Which means the near-term trajectory of Pluto's atmosphere is arguably less settled today than it was assumed to be a decade ago, not more. Confirming the haze mechanism answered one 8-year-old question and immediately became a key input into a second one that nobody has finished answering, and it will likely take another spacecraft flyby, decades from now, to settle it for good. Zoom out from Pluto for a moment, and there's a pattern here that shows up again and again across the history of planetary science. A single spacecraft flyby in 2015 handed scientists a number that didn't fit their model. Instead of forcing the data to match the existing framework, a small team spent 2 years building an entirely new explanation, one that made most of their peers skeptical at first. That explanation only became real science, rather than an interesting guess, because it was specific and falsifiable enough to make a prediction, one that couldn't be tested for another 5 years, because the instrument capable of testing it hadn't launched yet. And it only got tested at all because a separate team spent years solving what looked, on paper, like a boring technical problem. How do you mathematically separate the heat signature of two objects sitting too close together in the sky? None of that is glamorous. None of it fits neatly into a single dramatic headline. But it is, more or less, how almost every genuine advance in understanding another world actually happens. Not a single flash of insight, but a relay race stretched across nearly a decade, handed from a spacecraft to a theorist, to an entirely different telescope built for a different purpose, to a team of researchers patient enough to untangle two overlapping signals one wavelength at a time. Think about what that means for how we should judge scientific claims in general. The version of this story that spreads fastest online skips straight from mystery to shocking discovery, with nothing in between. No failed attempts, no years of ambiguity, no honest acknowledgement that for a long stretch of time nobody could actually tell what they were looking at. That skipped middle section is not a boring technicality. It is the actual work. Every real scientific claim that survives scrutiny has a version of that 8-year gap buried somewhere inside it. The unglamorous stretch where a good idea sits untested, waiting for the right instrument, the right technique, or the right patient team to finally catch up to it. And what most people are not seeing when a headline promises an instant answer is that the instant version is almost always the one worth being skeptical of. This is not a case for cynicism about science. It is closer to the opposite. A case for trusting the slow version more, precisely because it survived years of the chance to fall apart and didn't. There is a version of Pluto that most people still carry around in their heads. A frozen, inert rock at the edge of the solar system, demoted, dismissed, essentially finished as a subject of serious science the moment New Horizons flew past it in 2015 and moved on toward the Kuiper Belt. That version of Pluto never actually existed, and it never really matched what New Horizons found even in 2015. The real Pluto has spent the last decade quietly running an atmosphere unlike anything else we've directly measured. A world where solid smog particles, not air, decide how warm or cold an entire planet gets, glowing faintly in mid-infrared light that took a purpose-built billion-dollar space telescope, the better part of a decade to even learn how to see clearly. There's a single frame buried in the New Horizons archive, taken as the spacecraft looked backward after its flyby was already over, in which Pluto appears as nothing but a thin, glowing crescent backlit by the sun, with layer after layer of haze visible as faint blue bands stacked above its horizon. A photograph nobody planned to be poetic, taken by a machine simply following its instructions to keep recording as it flew away. That image was the first real evidence anyone had that the haze was even there in visible quantities, years before Zhang ever put a number to what it was doing. Somewhere above the same frozen nitrogen surface right now, at this exact moment, in the ordinary course of its 6.5-day rotation, that haze is still doing exactly what Zhang described in a paper almost nobody took entirely seriously in 2017, absorbing a whisper of distant sunlight and quietly radiating it back out into the dark, one particle at a time, whether or not anyone on Earth happens to be watching. So here's everything in one breath. New Horizons found Pluto's atmosphere 30 degrees colder than gas-based models predicted back in 2015. In 2017, Xi Zhang's team proposed that solid haze particles, not gas, were controlling that temperature, and predicted a specific mid-infrared signature that could prove it. JWST launched in 2021 with exactly the sensitivity needed to check, but spent years unable to separate Pluto's heat signal from Charon's, until researchers led by Tanguy Bertrand finally untangled the two and confirmed the haze signature directly, a result published this year in Nature Astronomy. Along the way, a second JWST team found carbon dioxide and hydrogen peroxide on Charon's surface for the first time. New proposals for further observations are due by September 30th, 2026, with fresh Pluto-Charon data potentially arriving as soon as July 2027. And whether Pluto's atmosphere ultimately survives its slow retreat from the sun or eventually freezes onto the surface is still genuinely actively unresolved. If this is the kind of story you want more of, real missions, real data, corrected instead of exaggerated, subscribe and turn on notifications, because the Cycle 6 results are coming, and I'll be covering them the moment they're public. Here's my question for you. Does the fact that this took 8 full years to confirm make it more impressive to you, or less exciting than a headline promising an instant discovery? Tell me which side you're on in the comments. I read every single one.